let's talk about the area of a surface of revolution now. So I want you to look at the picture we have here on the left. And in orange, we have this curve y equal to f of x. And I want you to imagine that we decided to take this curve, we decided to rotate it about the x-axis. So when we do take this curve and we rotate it about the x-axis, we're going to get a three-dimensional surface. The surface is going to be hollow, and our goal is to figure out what is the area of this hollow surface, okay? So the problem we want to investigate next is the surface area obtained by revolving a curve about the x-axis. And we want to mimic the ideas that we used when calculating arc length in the previous section. So we are going to follow the same basic strategy that we used earlier. I call this the basic calculus idea. The first thing we do is we chop up the interval AB into n pieces, okay? And what we're going to do is we're going to approximate, instead of a little bit of arc length, we're going to approximate a little bit of surface area this time. All right. And the total amount of surface area is going to, we're going to call that surface area A, and that's going to be approximately equal to the sum of a finite number, let's go from 1 to n pieces of a little bit of surface area. Okay. So once we've got our approximation consisting of a whole bunch of little bits of surface area added together, then what we're going to do is we're going to take a limit as n goes to infinity. And this will give us the true surface area. The true surface area. All right. So what we want to do in this video is we just want to break this down and get a formula for what we're trying to calculate here. And our formula is going to involve an integral. So we're really looking to get an integral at the end. So I want you to take a look at this picture I've drawn here. Here is our curve, y equal to f of x in orange. And I want you to imagine that we've chopped this curve up into pieces. And one of the pieces we have is right here. So this little cone-shaped thing is going to be that little bit of surface area I was talking about previously. Okay, so here's what we want to do. I want to take this cone right here, and I really want to imagine that I've taken this cone and I've cut it apart. All right, and when I cut it apart and I unroll it, I'm going to get an object that looks like this. So I'm going to draw a little rectangle here that looks like this. Now, this picture was drawn to look a little like really thick, like this delta x is a thick amount over here. But in reality, this delta x is going to be very, very small. It's going to be a very thin strip. And when we cut it, let's say we cut it here and we unroll it, we cut it and we unroll it, we're going to get something that basically looks like a rectangle. And when I think about what this rectangle looks like, what's the length of this rectangle from here to here, that's really going to be the circumference. Okay, and as we know, the circumference of a circle is given by 2 pi r. all right? And the next thing we want to worry about is we want to worry about what's the width of this strip right here. And the width of this strip is really going to be captured by a little bit of arc length. So we saw that in the last section that a little bit of arc length is abbreviated with ds. So this is a little bit of arc length. Okay. So what we're working with is we're really trying to figure out what happens when I try to calculate the area of a strip. And that is approximately equal to the area of the rectangle. So the area of the rectangle is going to be given by 2 pi r, which is the length, times a little bit of thickness ds, which is the width. And what we want to do is we want to unpack what that expression is and really get a formula. Okay. So let me unpack this a little bit. The 2 pi is going to be there as a constant. What's the radius going to be? So if we look over here, do you see how I wrote f of xi minus 1? That's really the left endpoint in my picture. And I have f of xi, that's really the right endpoint, the y value of the right endpoint and the y value of the left endpoint. And the radius that we're going to be working with is some height in between those two. It might be the left endpoint, it might be the right endpoint, it might be something in between. So we're going to represent this radius with f of xi star. And we know that this xi star exists from the mean value theorem. We had discussed this idea when talking about arc length. So that's going to, xi star is going to be something in between xi minus 1 and xi. And that's going to give us the radius that we're looking for, which is really going to be the y value of a function evaluated at some point. Okay. In the previous section, we also had the formula for a little bit of arc length. So that little bit of arc length is going to be given by the following. That's going to be 1 plus f prime of xi star quantity squared and times the delta x. So our surface area is going to approximately be equal to the sum, the finite sum, as I goes from 1 to n. We're going to add together the area of a bunch of strips. So this will be 2 pi f of xi star, the square root of 1 plus f prime of xi star squared delta x. Okay, that's the surface area. So that's just an approximation. We approximate it with a finite number of strips. And the actual surface area is going to be equal to what happens when we take the limit as the number of strips goes to infinity. Now, as the number of strips goes to infinity, that's going to make this width narrower and narrower and narrower. So our surface area is going to be equal to the limit as n goes to infinity, the sum as I goes from 1 to n, 2 pi f of xi star times the square root of 1 plus f of xi star squared delta x. And now that we've expressed our surface area as a limit, we can remember that this basically defines a definite integral. Sigma is the Greek letter for s, so let's put an s there. You're going to have 2 pi times f of x times the square root of 1 plus f of x, f prime of x squared dx. Delta is the Greek letter for d. And we want to indicate the endpoints. So let's integrate from a to b. And we could call this a. That's going to represent our surface area. So let me highlight this formula for now. And we will talk more about this surface area stuff in the next video. Take care, everyone.